Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be going over double integrals over rectangular regions. Firstly, I'd just like to talk about what exactly a double integral is. Well, a double integral is essentially a multivariable integral. We're going to be integrating now instead of just one variable, dy or dx. Well, we're going to be integrating now in dy, dx, or dx dz, or whatever, really. It's just multiple variables, so it's multivariable integrals subject to some region, right? Well, let's go ahead and talk about the rectangular region aspect of this. Well, what is a rectangle one-dimensionally? Well, it's some kind of shape that is restrained by some x of a and a b value. And similarly, it is constrained by R, C, and D in the y direction. Well, that's what our rectangular looks like. Well, what if we wanted to find the volume of a rectangle in 3 dimensions? Well, pretty much what we're going to be doing is we're going to be popping that baby into 3 dimensions, right? So before we start talking about exactly what a rectangular region is in 3 dimensions, I'd like to talk a little bit more about what exactly a double integral is and what exactly it does, because it's pretty important here. So I guess, what are we doing here? Well, we have some kind of function. Admire the beautiful drawing. Well, what is this? We're having a function saying we want to, well, perhaps we want to find the volume of this function right here. Well, what are we going to do? We're going to be making a bunch of rectangles, essentially, with sub-rectangles within them, making them increasingly smaller and smaller. And what is the base area of one of these rectangles? Well, in blue there, it is delta y times delta x. That's our base, right? Well, we need to extend that up to whatever height we need. And what we're doing here is we're essentially making a sum of all of these rectangles with our dA, or our delta A, our change in A. And well, what would happen here is, well, let's just go ahead and take a limit as our n goes to infinity. Well, what is that? That's going to be our integral definition there. We're just slicing up all of these rectangles into infinitely small pieces, all of these boxes, and now we are going to get our integration. So that's essentially what a double integral is over some kind of function. Well, what's a rectangular region? A rectangular region, well, instead of that curvy function right there, well, we're pretty much just going to have a big rectangle in our 3 dimensions there. So yeah. The y, well, what's our intrinsic motivation behind this? Well, I definitely gave it away already, but it's really just volume as of right now. Now, when we get into higher integrals, so we're getting into triple integrals, we're going to be discussing more, but mostly for right now, it's just going to be volume. How are we going to do this? Well, I kind of said it over here. Well, what happens here is if we take that limit of that sum, well, we're going to get 2 integrals, one. I'm not gonna get into that yet. I'm gonna bite my tongue on that one. How we're gonna do it is just offering a pretty simple definition here. We're gonna have some region R of our function in x and y times our dA. Well, what's that dA? That dA is gonna be split into dy, dx, or whatever 2 variables you're integrating. In this case, it is going to be dx and dy. How are we going to compute this is something I'll get into further in just a little bit, but what this is called is it's a double integral of our function f over our region R. We're integrating with respect to the area of our rectangles here, our increasingly small and infinite rectangles under our region of integration. So, just coming over here, procedurally, how are we going to do this one? Well, to compute a double integral, these are 2 iterated integrals, right? It's an integrated integral. So essentially, we're going to integrate an inner integral here. So what are we doing here? We're going to integrate this right here, just in dy, right? After we integrate in dy, do our fundamental theorem of calculus, we are going to be integrating in the outer variable now. So what are we going to be doing? We're going to be doing this integral with our dx. Easier to show rather than to explain for sure, but essentially what we're doing is treating any variable other than r with respect to variable as a constant, a fixed constant, just like we did in partial derivatives, but we're just doing it inversely, if that kind of makes sense here. Well, let's just go ahead and I'll stop yapping here and let's just go ahead and do one of these bad boys. So, what are we going to do first? Well, like I said, we're going to be doing this inner integral first. Didn't do that very well. We're going to essentially be doing that inner integral first, so let's just go ahead and do that one. Well, I'm just going to put that there. Conceptually, well, we have the integral of 0 to 1 of x, y, dy. Well, how are we going to do this? Recall in partial derivatives, like I just said, we're treating this x right here as a fixed constant. It's the same thing as 2, 3, 4, 5, whatever. It's a fixed constant, right? So what are we going to... It's pretty much just a simple integral if we just look at it that way. This is just going to be the integral of 0 to 1 of some x naught times y dy. Well, if we look at it that way, then it's going to be a lot simpler to solve. We're just going to be going ahead and doing the reverse power rule, right? We know how to do this one. This is something that we've been doing for the entirety of calculus. As long as we've been doing integrals, this is just going to be 1/2 xy squared from y is equal to 0 to y is equal to 1. Plugging in that y is equal to 1 and our y is equal to 0, well, that's just going to be 1/2 x times 1 squared minus 1/2 x times 0 squared. That's going to equal 1/2 x. We solve that inner integral now, so this right here is now going to become the integrand for our outer integral. So what are we going to do? We're going to rewrite our outer integral bound, which is 0 to 1 of this new integrand, 1/2 x dx. Once again, pretty simple integral here. We have 1/4 x squared from x is equal to 0, x is equal to 1. Fundamental theory of calculus, 1/4 1 squared minus 1/4 0 squared. That is going to equal 1/4. That's how you solve that procedurally. Why I am doing y is equal to 0, y is equal to 1 right here, and x is equal to 1, x is equal to 0 right there. Well, I'm doing that because when we don't split them up, when we're not just doing it that way, when we're writing it in one cohesive thing, well, when we have more difficult integrals here, the last thing we need is to plug in 1 into our x when we don't mean to, or 0 into our x when we don't mean to. So when you're first starting out doing these double integrals, triple integrals, it can be definitely helpful to specify what variable you have in your function being what value. Definitely something that can be useful there. One other quick note really fast is a kind of quick sanity check here, just to make sure we're doing this right. Well, when we're done with that inner integral, we should only have constants and or variables in our differential, right? So basically what I'm trying to say here is if I had any y's left over here, I messed up. Right? Because how am I gonna compute that? Then instead of having a value, these are definite integrals, we need to have a value come out of these. Well, if I had a y in there, then I guess I'm sure you can imagine that would be problematic, because then I would have 1/4 y. So I would have y over 4 be the output of this double integral, which is not correct. So I guess sanity check, halfway point here. Let's solve the inner integral. If I have the x or the y, just one variable, in the outer integral. Sorry, I'm explaining this poorly, but I'm trying to say do not have multiple variables for right now in these double integrals. Once you're done with that inner integrand, that's going to mess it up. You are not going to get the right answer, and let's just say you messed up somewhere for sure. All right. I split that first example up, so we're just going to go ahead and do it cohesively for this one. Maybe this is more of a motivation of why we should do this. Y is equal to 0, y is equal to 1, or x is equal to 0, x is equal to 1, or whatever. This may be more of a motivation here when we're kind of making it more advanced, more variables here. So let's just go ahead and do this. Well, what is this equal to? Well, we have our integral here. The integral from 0 to 2 of 16 minus 2x minus y dy. Pretty simple integral here. Treat that x as some fixed constant. We have from 0 to 1 of 16y minus 2xy minus 1/2 y squared. We are evaluating that. Oops. We are evaluating that from y is equal to 0, from y is equal to 2, dx. So let's just go ahead and plug in our, oh, that's not 16. Yeah, there we go, sorry. I messed that one up just slightly. We're good. All right, 6y minus 2xy minus 1/2 y squared. I apologize. We're going to have that integral from 0 to 1 on our outside, and then we're going to have 6 times 2 minus 2 times x times 2 minus 1/2 times 2 squared. Minus, that's going to be 0, that's going to be 0. As you can see, if we plug in 0 here, that's going to be 0, that's going to be 0, that's going to be 0. Multiplication by 0 minus 0 dx. So just simplifying this a little bit further, we are going to have the integral from 0 to 1 of 12 minus 4x minus, well, 2 squared is 4. 4 over 2 is 2. So we're going to have 2 dx. Simplifying one more time even further, we're going to have the integral from 0 to 1 of 10 minus 4x dx. Simple integral yet again. This is definitely calculus 1, calculus 2, what we're doing here. I'm not even going to write another integral sign. We are going to have 10x minus 2x squared from 0 to 1. Fundamental theorem of calculus here. We're going to apply that. We're going to have 10 times 1 minus 2 times 1 squared minus, we'll write this one out this time. Why not? 10 times 0 minus 2 times 0 squared. That's just going to be 0 right there. We're going to have 10 minus 2, which is going to equal 8. That is the final answer to our integral here. So I suppose a question that you might be having, although you can't ask me in person yourself, are these reversible? So I've been integrating in dy dx. What if I wanted to integrate in dx dy? Well, sometimes that can be beneficial for sure. Which is actually something that we're going to talk about later on when we need to figure out what order we want to differentiate in, because sometimes it can either be very difficult or borderline impossible if we integrate in a specific way, right? So for example, if we had the double integral of, well, let's just say our integrand is e to the x squared dx dy, well, that's going to raise a problem. We can't do that, right? That's gonna be pretty big problem there, and I think I'll do one more example to kind of motivate us that some orders may perhaps be better than other orders. But really fast, I just want to talk about, you can indeed, when we're talking about rectangular regions, that is, for right now we can switch the order. These are interchangeable in order. It's going to give us the exact same question, or it's going to give us the exact same answer here. Perhaps more difficult in other orders than others, but technically speaking, we can switch dx dy. We just have to switch our bounds of our integration. So using this second example here, well, what if I wanted to integrate this in dx dy? Well, what are we going to do here? I'm just going to change my bounds. Same integrand. Different differentiation, we're going to do dx dy this time instead of dy dx. Well, last time our dy integral had the bounds of 0 to 2. That is our outer integral now, so we're going to have this from 0 to 2. I'm going to speed through this one, by the way. And then we had our outer integral had the bounds of 0 to 1, so we're just going to change our bounds now as well. Integrating in dx, we're going to have 0 to 2 of 6x minus x squared minus yx from x is equal to 0, x is equal to 1 dy. That is going to be from 0 to 2 of 6 minus 1 minus y dy, which is going to be 5 minus y dy. Pretty simple integral here as well. We have 5y minus 1/2 y squared from 0 to 2. We're going to have 10 minus 2, which is going to equal 8. Sorry if I sped through that one a little bit fast, but I just wanted to make it clear that when we're talking about rectangular regions, the order does not matter. We can do it whichever way we want, and like I said, a motivation behind perhaps changing what was given is it may be borderline impossible and or very, very difficult to integrate if we were in one order compared to another. So let's just go ahead and have a driving example for that. So perhaps a little bit more of a difficult integral than we're used to seeing, especially on a third example for our double integral. We're going to have the integral from 0 to 1 and the integral from 0 to the natural log of 2 of y e to the x y dy dx. Well, just looking at this, well, we see a y multiplied to e to the y. Well, in our differential is dy. Perhaps we're familiar with this. This is going to be IBP. We're going to need uv minus the integral of v du, and or we could use the tabular method here for sure. But regardless, it's going to be a fair amount of work compared to, well, what if we just switch the order? These are 4 constants in our borders, our boundaries. This is 0 constant, 1 is a constant, 0 is a constant, natural log of 2 is a constant. Even though it looks fancy, it's still a constant. Natural log of 2 is going to give us a value. Well, what can we do here? We can just switch the order, which is pretty neat. So this is definitely going to be something that's going to be coming in handy for sure. Especially, once again, like I said, if we had some kind of case where we had like e to the x squared dx dy. Well, we can't do that, unfortunately. And that's definitely something that I'll get to in our next video when I'm talking about non-rectangular regions, where we're going to have to switch the order. We're going to have to figure out how to do that. But as for right now, sorry, I digress. We're going to switch our bounds, so we're going to have the outer bound be from 0 to natural log of 2, and our inner bound be from 0 to 1 of the same integrand, y e to the xy dx dy. Well, although it doesn't look much different, it's very different. What are we doing here? We're essentially just taking the integral of e to the x, right, to times some value, of course, but nothing that we're not used to. So what is the integral there going to be? Well, we're treating our y's as some kind of fixed constant. So therefore, what is the integral of e to the 2x, for example? Well, that's going to be e to the 2x over 2. So what is this going to be? This is going to be equal to y e to the xy times 1 over y. And we are going to have our x equal to 0, x equal to 1 dy. Plugging in those values, we are going to have 0 to the natural log of 2. Well, this is just going to cancel out. I can already see that. So we have e to the xy evaluated from x is equal to 1, x is equal to 0. Well, this is going to be e to the y minus e to the 0, which is 1 dy. Nothing else to actually mess with there. Pretty simple integral here. E to the y minus y from 0 to the natural log of 2. E to the natural log of 2 minus natural log of 2 minus e to the 0 minus 0. Well, e to the natural log of 2, that's the same thing as 2, right? So 2 minus the natural log of 2 minus 1. That's just going to be 1 minus the natural log of 2. That's our answer for this integral. And as you can see, it would have been a lot more difficult, or at the very least, a lot more steps. Obviously, difficulty is subjective, but I personally much prefer that one to having to do a tabular and or uv minus v du. Perhaps even twice we might have had to do it later on. But point is, maybe that's motivation for changing your differential, changing the order of your differential from dx to dy or dy to dx. And this is something that you can do whenever you have any kind of integral realistically, but it does get a little bit more complicated later on than just switching the bounds. That's the topic we'll get into in a lot deeper depth, because that's kind of fundamental when we're doing these integrals, when we're doing triples and more complex doubles. That was double integrals over rectangular regions. Thank you.